Okay, this is the continuation of the trig review lesson. We're going to look at some properties of the trig functions. I'm going to start with the obvious ones, which is domain and range. The trig functions are indeed functions, so they have a domain and they have a range. All right, so let's look at sine and cosine first. All right, as far as sine and cosine go, in terms of what I can put into the function for the angle, I can put anything I want in there. So for sine and cosine, the domain is just all real numbers. All right, the range is kind of interesting. I have a nice unit circle here, not like the one that I drew before. Let's take a look at the sort of outputs we get. All right, that's a little bit more important than the sort of inputs that I can put in. All right, if I look at all of the output values, let's look at sine first, the sine function. All right, so over here, the sine is 0 when theta is 0. The sine is 1/2 at pi over 6. Rad 2 over 2 at pi over 4. Rad 3 over 2 at pi over 3. And then at pi over 2, it's 1. All right, that is the largest value that the sine function can take on. All right, as I move this way, the values start decreasing again back to 0 at pi. All right, and then they start becoming negative, increasing in the negative direction as I move towards 3 pi over 2, at which point the sine function is -1. And then as I move back this way, you'll notice the negative values start, negative values would be increasing towards 0. All right, so what I get from this, is for a function y equals sine of theta, all right, that theta can be anything, right? All real numbers. All right, and y is going to be between -1 and 1. Now remember, these functions are cyclic, so basically the sine function bounces between -1 and 1 as the graph continues. So it's probably worth at this point actually looking at the graph, a basic graph for sine of theta, and then we can point out some of the properties of it. All right, so I'm gonna draw kind of a lopsided axis here. And what I'm gonna do is I'm gonna put the unit circle values for pi over 2, pi, 3 pi over 2, and 2 pi over here. All right, and then 0's right here. So let's look at one revolution of the unit circle. All right, so at 0, the sine of 0 is 0. So that point is right here. At pi over 2, right, the sine of pi over 2 is 1. So I need to, let me do this. All right, so at pi over 2, the sine is equal to 1. At pi, right, come back over here at pi, the sine is 0 again. At 3 pi over 2, the sine is -1. And at 2 pi, I don't have 2 pi written in there. At 2 pi, I'm back at 0 again. All right, so for one revolution of the unit circle, what I get is this. All right, that didn't cross where I wanted it to. Let me try that again. Try to be a little more careful here. My graph isn't really to scale. I'll show you a better picture before. Okay, we get that kind of shape, right? That kind of up and down shape like that. This is a poor representation of it. Okay. All right, now here's the thing. I could keep going around the circle again and again and again, right? I just keep adding angles to it. So from 360, I would add 30 degrees and be at 390, or 2 pi and add pi over 6, like that, pi over 4. So this keeps going forever and ever and ever. This direction keeps going forever and ever and ever in that direction, bouncing back and forth between -1 and 1. All right, now, when we look at just one revolution of the unit circle, I'm going to keep doing this until I get something roundish. All right, all the way around. That is called one cycle of the sine curve. So one cycle of the sine curve is when theta is between 0 and 2 pi. All right. That cycle repeats itself over and over and over again, but that is considered one cycle. All right. We refer to the length of that cycle as the period of the function. And the period of the sine curve is 2 pi, because we get one cycle between 0 and 2 pi. All right, now I can do something similar for cosine. If I get a blank page here, I can do something similar for cosine. All right, if I take y equals cosine theta, right, again, the domain is the same as sine. Right, so theta can be anything at all. The range is also the same as sine, between -1 and 1. Okay, so if I draw, again, we'll pretend these are straight lines, and I put my markers in, my axis markers in again. All right, if we follow the unit circle around for cosine this time, the x-coordinate, at 0, cosine is 1. The values for cosine decrease as I head towards pi over 2, where cosine becomes 0. All right, and then the values continue to decrease to -1 when the angle is pi. All right, and then they turn around and start to increase again until I get to 0, and then they continue to increase again until I get back to 2 pi. So if I put these points, transfer these points over here to my xy axis, when the angle is 0, cosine is 1. When the angle is pi over 2, cosine is 0. At pi, cosine is -1. 3 pi over 2, it's 0 again. And at 2 pi, it's back at 1. All right, so what I get is this kind of, all right, apparently I'm better at drawing cosine curves than I am at drawing sine curves. All right, I get that shape there. All right, now again, this is going to repeat over and over and over again. All right, so one cycle of the cosine curve is where theta is again between 0 and 2 pi, and the period, the length of one cycle, is 2 pi. All right, now one of the things you might notice if I switch back and forth between, let's see if I can do this. If I switch back and forth between my sine curve and my cosine curve, is that they look similar. It's hard to tell from my drawings, I realize. They look similar, all right? One is shifted. If I were to take my sine curve right here and shift it so that this point was here, I would have a cosine curve, right? It would be this part right here. right in there. All right, so the cosine curve and the sine curve are definitely related to one another. And in fact, they are shifted 90 degrees from each other. All right, which is another property that we can talk about. All right, so you have your basic sine curve and you have your basic cosine curve. I'm going to show you these on the calculator in a minute too. All right, now a couple of things we can look at based on the unit circle and based on the two graphs. All right, and that is, we've talked about functions being even or odd. Right, so if I come back here and I look at my sine curve, let's take a look at what the sine curve looks like, right? If you look at it on this side of the y-axis, and you look at it on this side of the y-axis, all right, that looks like it has the property of being an odd function, of being symmetric about the origin. And in fact, if you take a look at the values, the way the sine values reflect, right, in the first quadrant, and in the second quadrant, and in the first quadrant, and the third quadrant, all right, they have that property of swapping signs. All right, so the sine curve, and I think I can sketch this in here. Do I have this? Yes, okay. So the sine curve has the property of being an odd function, which means that the sine of negative theta is the same thing as negative sine of theta. All right. If we switch over to the cosine curve here and take a look, if I were to continue this like I did the sine curve and I were to make it go down here, and then it would do that. All right, this looks a lot like it's reflected over the y-axis. All right, which would make this an even function. All right, so the cosine curve is an even function, which means that cosine of negative theta is equal to cosine of theta. All right, so now we have some function properties for both the sine function and the cosine function. Now we can translate all this to the other trig functions. I'm not ready to graph them yet, so I'm not going to do that yet. All right. Okay, so let's take a look at. All right, so there's a little table here again on page 396 in your book that talks about the domain and range of all of these. Okay. Let me get a clean page here and we can sketch some of this out. All right, so we know the domain and range for sine and cosine. Now let's think for a minute about tangent, cotangent, secant, and cosecant. They are all defined as the ratio of other trig functions. That makes them rational functions. If we start with tangent, tangent is sine theta over cosine theta. That is a rational function. That means anywhere where cosine theta is 0, tangent will have an asymptote. Right, so when I look at where is cosine of theta equal to 0, I go back over here to the unit circle, and I say, well, cosine is 0, well, right here at pi over 2, and right here at 3 pi over 2. All right, so this is going to be when theta is pi over 2, 3 pi over 2. Now, if I were to continue going around and around and around, because remember, these functions are cyclic, I would be up here again, and at that point it would be 5 pi over 2, 7 pi over 2, ... Okay? But also in the negative direction. All right, so negative pi over 2. Negative 3 pi over 2, because remember, cosine is even. Negative 5 pi over 2. dot, dot, dot. All right. So when we look at one cycle for tangent, right? One cycle for tangent, we pick two asymptotes and say one cycle exists between those two asymptotes. Now we could pick pi over 2 to 3 pi over 2, or I could pick negative pi over 2 to pi over 2. The standard for tangent is negative pi over 2 to pi over 2. All right, that's just the way we do it. All right, and that makes the period for tangent, notice, the distance between negative pi over 2 and pi over 2 is pi. So the period for tangent is pi. The same for cotangent, however, all right, cotangent is cosine over sine. Cosine theta over sine theta. So that means that the cotangent is going to have asymptotes where the sine of theta is 0. So sine of theta is 0. When theta is, well, let's take a look, 0, pi, and if I were to keep going around, 2 pi, 3 pi, 4 pi, 5 pi, right? So 0, pi, 2 pi, 2 pi, 3 pi, dot, dot, dot. Same thing in the negative direction, right? 0, negative pi, negative 2 pi, dot, dot, dot. All right, so one cycle for cotangent, again, we want between two asymptotes, so for cotangent we go between 0 and pi. All right, so it's going to be 0 and pi, and again, the period here is pi. All right, now both tangent and cotangent are considered odd functions because sine is odd and cosine is even. So when you put the two of those together, you're going to get an odd function. All right. Okay. All right. So then I'm just gonna talk through secant and cosecant because I'm not ready to look at the graphs of those yet. All right. So the secant function is 1 over the cosine function. So the reciprocal of that, so anywhere where cosine is 0, secant is going to have asymptotes, and cosecant is 1 over the sine function. So anywhere where the sine is 0, cosecant is going to have asymptotes. They both have a period of 2 pi, okay, because they are based solely on a single other trig function. So there's some information here about the period on page 397 you can take a look at. And this is just quadrant information. Here's where I want to get to. Now, we talked about these because I've been using them. All right, these are the reciprocal identities. That's what they're referred to, right? The reciprocal identities and the quotient identities. Now, we have an additional set of identities for, excuse me, for sine and cosine and the others, all right, that are based on the fact that these trig functions are based on a circle. All right, so remember, we have a circle of radius 1. So a circle of radius 1 is going to have an equation that looks like that. X squared plus y squared equals 1. Well, we already know from the unit circle that points on that unit circle can be defined in terms of sine of theta and cosine of theta. So the x is cosine theta squared. The y is sine theta squared. All right, now there's a little shorthand notation for writing this, which is to say cosine squared theta. Sine squared theta equals 1. All right, this is an important trig identity. In fact, if I had to tell you the most important trig identity, that would probably be pretty close to the most important trig identity you're going to get. All right, it comes directly off the unit circle. All right, and what it means is no matter what theta is, if I have that form, then I have 1. So if I have, I don't know, cosine squared of 21 degrees plus sine squared of 21 degrees, what am I going to have? I'm going to have 1. All right, no matter what theta is there. Now this is referred to as the Pythagorean identity. All right, so from this Pythagorean identity, I can derive 2 other forms. One involving tangent, the other involving cotangent. And here's how you do this. All right, you start with the basic Pythagorean identity. Now let's say I need the version that involves tangent. So tangent is sine over cosine, so I'm going to divide everything in this equation by cosine squared theta. What do I have here? I have 1 plus tangent squared theta equals secant squared theta. Here is a second form of the Pythagorean identity. All right. And the third one is going to come basically the same thing, only we're going to divide by sine. So if I start with cosine squared theta plus sine squared theta equals 1, and I divide by sine squared theta, all right, cosine theta over sine theta is cotangent, so that is cotangent squared theta. That's 1. This is cosecant squared theta. Here is the third form of the Pythagorean identity. Now, do you have to memorize all 3? No. You have to memorize this one. And then just know how to get from here to here and from here to here. All right? If you need the one for tangent, just divide everything by cosine. If you need the one for cotangent, divide everything by sine. Okay, so you don't need to memorize all 3, but you do need to know the first one there. Okay, I believe at this point there are the Pythagorean identities, and I think that's all I need to go over here. Okay, so what I want you to look at here, and here, okay, here are the even-odd identities. Okay. All right, so for section 6.3, take a look at the problems on page 405. Number 11 through 58, I think, is good. And I'm going to stop this video, and we'll continue with all of the trig graphing stuff in the next video.